Hello, this is Dr. Joe Treff from the physics program at Stockton University. In today's lecture, we're going to talk about some of the moons which circle some of the planets in our solar system, and about the planet, or the not a planet anymore, Pluto. So this is chapter 12, Rings, Moons, and Pluto. So if we look at the Jupiter family, and this shows pictures of the moons, which have been assembled from individual Galileo and Voyager pictures. And it shows the family portrait of Jupiter with its giant red spot. And it's 4 moons. And from the top to the bottom, we see Io, Europa, Ganymede, and Callisto. And the colors are exaggerated by image processing to emphasize the contrast. So here shows the moons of our solar system, and this image shows some of the selected moons of our solar system and their comparison to the size of the Earth's moon and the Earth itself. So see here we see the Earth, and here we see our moon, okay? And here's the moons of Jupiter, so Io, Europa, Ganymede, and Callisto. And the 1, 2, 3, 4, 5, 6, 7, 8, 9 moons of Saturn, and the moons of Uranus and Neptune. And also shown here is Pluto and its moon. Sorry, it's shown as Pluto's moon. If we look at Callisto, it's Jupiter's outermost large moon, and it shows a heavily cratered surface. And we believe this is mostly ice, while the darker areas are more eroded, ice-poor material. So these high-resolution images were taken by the Galileo spacecraft in 2001. And it shows the icy spires on Callisto's surface. And you see the darker dust that has slid down from the ice erodes, and it's collecting in the low-lying areas. And these spires are about 80 to 100 meters tall. And as the surface erodes even further, the icy spikes eventually disappear and leaving impact craters exposed. And these are shown in the lower image. If you look at Ganymede, right, this is the largest moon in our solar system, and this picture was taken by Voyager 2. And the colors, once again, are enhanced to make spotting differences easy. So the dark places are older, more heavily cratered regions, and the lighter areas are younger. And this is the reverse of our moon. And the brightest spots are sites of geological recent impacts. The close-up of the Nicholson Regio on Ganymede shows an old impact crater. It's on the lower left-hand side, and it has been split and pulled apart by tectonic forces. So against Ganymede's dark terrain, a line of grooves and ridges appear to cut through the crater that's forming its circular shape. There's some evidence for an ocean on Europa. So this is a close-up of an area called Connemara Chaos, and it's shown here with an enhanced color. And this view is 70 kilometers wide in its long dimension. So remember, 10 kilometers is about 6 miles, so this is about 42 miles wide. And it appears that it is a region where Europa's icy crust is, or recently was, relatively thin, and there it is easier to access to the possible liquid or slushy ocean beneath. So it's not anchored to the solid crust underneath, and many of the ice blocks here seem to have slid or rotated from their original position. In the high resolution view in picture B, the ice is wrinkled and crisscrossed by these long ridges. And where the ridges intersect, we see which ones are older and which ones are younger. And the younger ones cross over the older ones. While superficially, this system of ridges resembles a giant freeway system on Europa, the ridges are much wider than our freeways and are a natural result of the flexing of the moon. So here we see a very high resolution Galileo image of one of the young double rings on Europa. And this area the picture is about 15 kilometers across. So once again, 10 kilometers is 6 miles. So this is about 9 miles across. And it appears to have formed when we have a viscous icy material was forced up through the long straight crack in the crust. So note how the young ridges are going from the top left towards the bottom right, lie on the top of the older features, which are themselves on top of even older features. Here shows two sides of Io, and this is a composite image, shows both the sides of the volcanically active moon Io. And the orange deposits are actually sulfur snow, and the white is sulfur dioxide. So the volcanic eruptions on Io are shown here, and this composite image from NASA's Galileo spacecraft shows close-ups of the two separate volcanic eruptions on Jupiter's volcanic moon, which is known as Io. And in the upper inset, you can see a close-up of the bluest plume rising about 140 kilometers above the surface of the volcano. So 140 kilometers is about 84 miles. So our atmosphere, at least the lower level, goes up to about 11 kilometers and about 21 at the equator. So this is much higher than that. And this is for the troposphere. And in the lower inset of the Prometheus plume rises about 75 kilometers from Io's surface. And this plume is named for the Greek god of fire. So here shows three photographs from April 1997 and September, and then July 1999. And it shows the volcanic changes on Io. And these three images were taken of the same 1,700 kilometers square region of Io in 1997, September 1997 and July 1999. And the dark volcanic center, called Filian Petra, experienced a huge eruption, producing a dark deposit some 400 kilometers across. And these are seen as the gray areas in the upper center of the image. And in the right image, however, some of the new dark deposit is already being covered by reddish material from the volcano. Also, a small unnamed volcano to the right of Pilian has erupted since 1997, and some of its dark deposits and young ring around it are visible in the right image. And this is to the right of the gray spot. Once again, the color has been exaggerated in these images by processing. Here shows lava foundations on Io. So Galileo captured a number of eruptions along the chain of huge volcanic pits on Io. And in this false color image, so this was a black and white image that was colored to show some of the different features, and it's combining infrared and visible light. So the bright orange yellow regions at the left are places where fresh hot lava is erupting up from the ground. Here we see 3 icy moons. So these are Europa, Ganymede, and Callisto at the same resolution. And note the number of craters, and thus the age of the surface we see increases as we go from Europa to Ganymede to Callisto. And Europa image is one of those where the system of cracks and ridges resembles a freeway system. Yeah, your music's this from here. Sorry, the radio just went on and I was turning it off. Okay, the structure of Titan's atmosphere, and this is another one of the moons. It shows resembles some of the features of the Earth's atmosphere, although it's much colder than our planet. So we're talking about a surface somewhere around 100 K, which is much colder than our surface. So our surface is about 293 K. So it's about a third of our surface temperature. And the red line indicates the temperature of Titan's atmosphere at different altitudes. So on our surface, what happens normally is that the temperature decreases until we get to the stratosphere, where the ozone layer can absorb solar energy, and then the temperature increases a little bit, and then it begins to decrease again, and then increase a third time out to the edge of our atmosphere. So this isn't quite like ours, but there are some similarities. So note that as we leave the surface, it cools, and then we have this region of methane or ethane, in which case can absorb the solar energy, and it starts to warm up. Okay, then unlike ours, it continues to warm up until the surface, right? But notice that even at the top of their atmosphere, where it's the hottest, is nowhere near our surface temperature. We also see some photochemical haze here, so where we get almost like smog, and we also see something that kind of looks like rain. It's at least particulate matter. Here shows views of the surface of Titan, and the left image shows the views of Titan from the descent camera, and in a flattened projection, and at different altitudes. And the right image is taken after the landing, and it shows the boulders that are all over the surface, and they're illuminated by this faint reddish sunlight. And the boulders are composed of water, of ice made from water. We also see some lakes. So the Cassian image taken in September of 2006 during a flyby shows the liquid lakes of Titan. And they're mostly a combination of methane and ethane. And since this is a radar image, the colors are artificially added. And the dark blue areas are the smooth surfaces of the liquid lakes, and the yellow is the rougher, solid terrain that surrounds the lakes. B shows a mosaic of Titan's surface from the Cassian-Huygens mission, and it shows in detail the high ridge area and many narrow channels that are formed by erosion and appear to be part of the widespread network of rivers carved by the flowing hydrocarbons. Here's Neptune's moon Triton, and this mosaic of the Voyager 2 images show a wide range of surface features. So the pinkish area at the bottom is Titan's large southern polar cap. And the southern polar cap of Triton faces the sun here, and the slight heating effect is driving some of the material northward where it's colder. And here we see a close-up view of some of the geysers on Neptune's moon Titan, with these long trains of dust pointing to the lower right in this picture. So here we see Pluto's motion and portions of two photographs by which Clyde Tombaugh discovered Pluto in 1930. And the left one was taken on January 23rd, and the right one on January 29th. And note that Pluto's indicated by the arrow has moved among the stars during those 6 nights. And if we hadn't put the arrows here, though, it would be hard to have spotted this dot moving through the atmosphere. So once again, note that the stars are pretty much stationary or appear stationary. However, Pluto has moved in reference to the stars. So here we see a comparison of the sizes of Pluto and its moon Charon and compared with the Earth. And this graphically vividly shows how the tiny Pluto is relative to the terrestrial planets like Earth, and that it is primarily the primary justification for putting Pluto in a class of dwarf planets rather than terrestrial planets. So that's one of the reasons it was moved down, because it's so much smaller than the Earth, and even its moon is comparable in size to it. Here's another reason. If you notice the orbits of all the other planets, right? They're kind of in this one, they're kind of in a single dimension or in this one area. And Pluto pretty much has a wildly different orbit. So that's another reason that it was moved to to give it a dwarf planet status. Although there is talk about making it a planet again, so we'll see what happens. So this is Clyde Tombaugh in 1906 to 1997, and he's pictured on his family farm with his 9-inch telescope, which he built. And he's looking through an eye, and at B, he's looking through an eyepiece at the Lowell Observatory. So here shows this haze layer on the atmosphere of Pluto, and it's one of the highest resolution photos of Pluto taken by the New Horizons spacecraft about 15 minutes after its closest approach. And it shows 12 layers of haze. If you look closely, you can see where they're starting to, you can see the differentiation between each one of the layers. And note also the range of mountains with its height up to about 3,500 meters. So once again, we know that 5 kilometers is about 3 miles, right? So this is about half of that. So let's call it about 1.5 miles. So here shows a global color image of Pluto. And this was also taken by the New Horizons. And it clearly shows a variety of terrains on Pluto. And the dark areas in the lower left is covered with impact craters, while the lighter areas in the center and lower right is a flat basin devoid of craters. And the colors you see are somewhat enhanced once again, so that you could see the features a little bit better. And it's to bring out these subtle differences. So here's a great picture showing the diversity of terrains on Pluto, right? So this, once again, is color enhanced, and it shows about an 80-kilometer long stretch here. So that's about 48 miles. And from left to right, we see a first cross a region of the Badlands with some of the craters showing. And then we move to the right, we arrive, and then across a wide range of mountains made of ice that's made from water and coated with the redder material we saw in the previous image. Then at the right, we arrive at the shoreline of a great frozen nitrogen lake, and this nitrogen sea is divided into mysterious cells, and we're not sure exactly why that is, and they're many kilometers across. So here shows some more images of the terrain on Pluto, and in this photo we see about 250 kilometers, and we can see the many different kinds of terrain. And at the bottom are the older cratered highlands and a V-shaped region of hills without cratering point towards the bottom of the image. And surrounding this V-shaped dark region is a smooth, brighter nitrogen plane, and these acting as glaciers on the Earth would do. So some of the isolated mountains are made of frozen ice water are floating in the nitrogen near the top of this picture. So in this scene, in B, we see that it's about 390 kilometers across, and the rounded mountains are quite different from those we know on Earth. And they're named Tartarus Dorsa, and the pattern's made of repeating ridges with the more reddish terrain between them, and they're not yet understood. If we look at Pluto's large moon Charon, the new horizon image, and once again, the color has been enhanced, and it brings out the colors of the moon's strange polar ice cap. And Charon has a diameter of about 1,214 kilometers, and the resolution of this image is about 3 kilometers. So here we see that the moon from its slightly different angle is in B, and this is true color. So this has not been enhanced in any way. And the insert shows about 390 kilometers from the top to the bottom. And near the top is left as an intriguing feature and what appears to be mountains in the middle of a depression or some kind of moat. So if we look at the 4-ring system, this diagram shows the location of the ring systems of the 4 giant planets. And the left axis represents the planet's surface, and the dots vertical line is the limit inside which the gravitational forces can break up moons. So each planet's system is drawn to a different scale so that the stability limits line up. The black dots are the inner moons of each planet, and they're on the same scale as the rings. And notice that the only really small moons survive inside the stability limit. So here we see the rings and their near moons, and this tidal stability to where if it gets inside of there, we'll see the moon start to break up. So here we see Saturn's ring. So A shows the view from above illuminated by direct sunlight. And B is illumination shown from below is sunlight that has been diffused through the gaps in the rings. Here we see an artist ideal representation of the rings of Saturn as seen from the inside. So note that the rings are mostly made up of pieces of water ice of different sizes. And at the end of its mission, the Cassini spacecraft is planning to cut through these one of these gaps in Saturn's rings, but it won't get this close. Here we see the image shows both smooth and cratered surfaces, cratered terrain on Saturn's moon, and also these tiger stripes in its southern polar region. And these dark stripes, and once again, the color has been exaggerated, have elevated temperatures and are the source of many geysers discovered on this planet, on this moon, excuse me. And they are about 130 kilometers long and about 40 kilometers apart. And shown here is the moon is shown to scale with Great Britain and the west coast of Europe, and emphasizes that it is a small moon, only about 500 kilometers in diameter. We also see geysers on this moon. So the Cassini image shows a number of water geysers on this small moon. And they're apparently salty waters from the subsurface source escaping through the cracks on the surface. Here we see the rings of Uranus, and the Voyager team has had to expose these images for a long time to get a glimpse of Uranus's narrow, dark rings. So you can see the grainy structure of the noise and the electronics of the camera. So in essence, it kind of is like leaving the shutter open for a really long time to get enough light to develop. But the problem is that then if there's any motion, it's going to blur the picture a little bit. So here shows the rings of Neptune, and this once again is a long exposures of Neptune's rings, and it was photographed by the Voyager 2 spacecraft. And note the two denser regions in the outer rings. So here we see Saturn's F-wing and its shepherding moon. So the moons are used to keep the rings in check. And this Cassini image shows the narrow, complex F-ring of Saturn and its two small shepherd moons, Pandora and Prometheus. And in the closer view, the shepherd moon's Pandora is about 84 kilometers across, is seen next to the F-ring, in which the moon is perturbing the main brightest strand of the particles. So it's believed that these shepherd moons actually keep these particles in place around the rings and create the rings, or keep the rings from like floating away. All right, well, thank you for your attention, and next we'll go to chapter 13.